I'd like to welcome all attendees of the current session. I'm going to present Simulation Use Case 2 to you together with Sonja Marahrens and Thomas Pajenkamp. Mrs. Marahrens works as an engineer for IPG Automotive in the team Engineering Research and Add-on. In set level, she's responsible for the integration of simulation use cases 2 and 3 in the IPG Automotive tool CarMaker. Mr. Pajenkamp is employed at dSPACE as a software developer in the department Engineering, Services and Pre-Development. Beside other numerous project tasks, he is responsible for the integration of simulation use case 2 in the dSPACE tools. In the next hour, you will learn the key facts about the simulation use case 2 as it is defined and implemented within the set level project. If you have questions, please use the Q&A chat on the website in order to place them. We will have time at the end of the session to answer a few of them. First, I'm going to introduce the general purpose of the simulation use case 2, as well as the specific simulation design, which has been implemented until today's midterm event. Current results will be shown and demonstrated with a focus on the specific contributions of the simulation use case 2 to the simulation-based development and testing of automated driving functions. A short outlook to the future content of the simulation use case 2 work will complete the presentation. As introduced in the first of today's presentations, the simulation use cases shall work as exemplary implementations of various project results and at the same time demonstrate a number of project goals. For example, the usability of relevant standards, especially regarding model integration and communication, and the application of a common development and documentation process. The SUC2, as I will refer to it in the following, is specified as a closed-loop simulation for integration test and validation. Hence, it is intended to be part of the later development phases along the V model, as depicted on this slide. As already shown on the previous slide, the main purpose of the SUC2 is the test and validation during function or system development. The most important aspect for the investigation of the system under test is the interaction with other components, which only appear within closed-loop simulations. For the current implementation, the system under test and test goals are chosen as examples for typical SUC2 simulation. In this case, a highly automated driving function acts as system under test, and the primary goal is to test its correct functionality. The test should comprehend the difficulty of incomplete sensor information, mainly due to temporarily occlusion of a relevant object. For the project of even higher importance is the simulation goal. SUC2 should implement a simulation based on various models from different sources, which are integrated using standardized interfaces, namely FMI and OSI. What these standards imply will be explained later on during the presentation. The credible simulation process shown on this slide has been introduced earlier today. In order to obtain a common documentation throughout the project and to enable traceability, this process has been applied in SUC2 as a guideline for the simulation development and to structure the course of action. On the following slides, the overall simulation design for the current implementation will be presented. Here, you see the scenario setup, which includes 5 road users, 3 passenger cars, a truck, and a pedestrian. The ego vehicle is controlled by the system under test, which is the highly automated driving function. All other traffic participants follow specific trajectories. The truck is going to turn left at the intersection. The pedestrian is aiming for the northern crosswalk. V2 and the ego vehicle shall turn right, and V1 is parking. The map for the traffic space was defined using the ASIM Open Drive standard, and the dynamic elements of the scenario were described using the ASIM Open Scenario standard. At the time t0, the situation is as depicted. By the time when the ego vehicle reaches the intersection at t1, both V2 and the truck are already performing their turning maneuvers. The next important moment is when the pedestrian has passed the crosswalk at t2. And finally, the ego vehicle reaches the crosswalk at t3. Especially the last 2 points of time are of particular interest because they are relevant for the first evaluation metric, the post-encroachment time, or PET. This metric describes the time gap between one road user leaving the interference zone with another road user, shown in the middle picture, and the second road user entering it, as shown in the right picture. These 2 points in time are equivalent to T2 and T3 of our scenario. The PET is a simple post-runtime metric which reveals the level of risk of the respective situation. The second metric is the time to brake criterion. The TTB is a more detailed metric for the criticality of the situation, as it continuously calculates the remaining time for a braking maneuver with a certain deceleration, a brake. The TTB is calculated along the ego trajectory. A TTB of 0 means that it is not possible anymore to brake before the interference zone. The simulation setup is implemented 2 times, using both the vendor tools from IPG Automotive and dSPACE. The integrated models are the highly automated driving function, separate models for the motion control and the vehicle dynamics, and 3 different sensor types. The listed standards have been applied. A few more details about the different models will be given on the next slides. As introduced, the highly automated driving function is the system under test. Hence, we will have a look on some basic aspects of its implementation. The highly automated driving function is composed as depicted and includes routing, localization, sensor fusion, object handling, and trajectory planning routines. A specified driving goal as well as odometric and object information serve as input data. The planned trajectory for the ego vehicle is the output of the function. For some of the inputs, the standardized OSI communication interfaces are used, which define the structure of the signals. Not yet standardized signals have been specified within the project following the OSI standard formats. The highly automated driving function is characterized by its object handling and the reaction to other road uses. The object tracking assumes constant velocity of tracked objects and incorporates timeouts. The highly automated driving function considers object classes and the relative position of the objects to the ego vehicle and the driving lanes within the calculated trajectory. The model is based on the intelligent driver model by Kesting, Driver, and Helbig, with an extension for tight cornering. The function is implemented as a modular and distributed system. It is based on ROS as a middleware, and it makes use of ROS-specific services. All sensor models are object-based and implement various effects like range, field of view, and occlusion. With these effects, typical sensor behavior is modeled on an object level, depending on the respective sensor technology. For the vehicle dynamics, a simple 2D one-track model controlled by a nonlinear controller is used. The simplification yields to a number of model boundaries. That limits the model's range of validity and leads to constraints in the usable tire road friction. The mounting positions of the different sensors can be seen in these illustrations. The sensor setup is shown. The camera is located behind the windshield and the other two sensors at the front of the ego vehicle. This slide shows an overview of the simulation architecture. Besides the different simulation modules, the vendor tools complement the simulation system. As already shown at the example of the highly automated driving function, the communication takes place following the OSI standard, supplemented by set-level specific signals. The model integration was done using another standard, the Functional Mockup Interface, or short FMI. Using this standard eases the integration and improves flexibility. Only the highly automated driving function couldn't be implemented as a functional mockup unit, hence a specific proxy serves as a gateway. All SMUs are marked with a red borderline in the architecture sketch. The simulation system in the upper left corner is embedded in a procedural context with pre- and post-processing elements. The pre-processing comprehends the generation of a number of concrete scenarios with individual parameter sets based on a basic reference scenario. Within the post-processing, the PET and TTB evaluation takes place. Different parameters have been modified in order to vary the situation and to specifically change two aspects. First, the duration of the occlusion regarding pedestrian detection. And second, the distance between the ego vehicle and the pedestrian when redetected after occlusion. For this purpose, the initial positions of the ego vehicle and V2 were varied, as well as the waiting time of the pedestrian when reaching the crosswalk. For the following demonstration of the midterm implementation, two specific parameter sets were selected. For the dSPACE demo, a scenario with long occlusion caused by both the truck and V2, but a good and timely sight on the pedestrian, and for the IPG automotive demo, a scenario with a shorter occlusion, but a late sight on the pedestrian due to an earlier arrival at the intersection and hence a tighter following of the truck. I will now hand over to Thomas Pajenkamp, who will present the first part of the midterm implementation results.
Sorry. Yeah, I'm going to show you the implementation and integration of simulation use case 2 in the dSPACE toolchain. And let's start with an overview of the dSPACE end-to-end simulation environment. Not all features of our toolchain are covered by the set-level project, but many important aspects are addressed. In general, scenario-based testing can be split into 3 stages, from left to right: preparation, simulation and interfacing, and testing. During preparation, all artifacts required for the testing task at hand are created, configured, and parameterized. Most importantly, this includes the scenario to run together with its road network, but also the external models, that is, sensor models, the highly automated driving function, and a vehicle model, which have been provided by our project partners. In the simulation and interfacing stage, the integrated vehicle, environment, and sensor models are run on the simulation platform together with the automated driving function as system under test. Thanks to defined technologies and interfaces, the building blocks can be combined easily. The final testing stage deals with the analysis of simulation results, especially the evaluation of test criteria like the time to brake and post-encroachment time metrics. Now we are going a little more into details. The road network and scenario are provided in the Open Drive and Open Scenario standard. And for the preparation, these are imported into the dSPACE toolchain via Model Desk. Originally, the first versions of both the map and the scenario have been created within our tools, but afterwards, the exported Open Drive and Open Scenario files have been adjusted so that they need to be re-imported into the dSPACE toolchain. Please also note that the road network and scenario will be made available under an open source license. Now back to our integration task. For the import of the Open Drive road network, the Model Desk road editor has been used. Likewise, the actions of the ego vehicle and all fellows defined in the Open Scenario file have been imported into the scenario editor. In the scenario editor, the action sequences of the individual traffic participants and the transitions between actions are visualized and can also be edited. This is shown on the slide in the lower right corner. This slide shows an overview of the final integration used for the simulation. Thanks to our preparation, the scenario with its different variants is already ready to use. The lower block shows the basis of the simulation, which is dSPACE ASM, which stands for Automotive Simulation Models. ASM provides the environment model and controls the scenario execution. External vehicle and sensor models, camera, LiDAR, and radar, are all integrated into the ASM model. Additionally, the automated driving function is running separately as an Ubuntu Linux Docker container and is connected to the ASM model via TCP. The overall model is running on the dSPACE VIOS platform for offline simulation. Information from the road network as well as the running scenario are used for the animation of the scene. See the top right. This animation can also be exported as a video file. Additionally, during the simulation, a trace file of ground truth simulation data is created for evaluation purposes. And then I would like to show you the actual simulation of one of our scenario variants. The scenario is animated in a 3D environment. And as you can see on the slide, the automated driving function provides some information for diagnostics in a console window. As a reminder, in the scenario, all fellows follow a trajectory, which also includes their timing. And the blue ego vehicle is controlled by the automated driving function. The mission of the driving function is to reach a specific point, and it must ensure safe travel, like staying on the lane at adequate speed, no collision, etc. To reach the target, the ego vehicle has to turn right at the crossroads. Now let's watch. So the ego vehicle starts with a velocity of 50 kilometers per hour. We can see the truck turning before the vehicle, and ego brakes when it approaches the crossroad. Now it must wait a bit to let the pedestrian pass, and after the turn, the pedestrian on the sidewalk can be safely passed. Let's rewatch the whole scene one more time. So as you can see, this scenario is not really critical because the ego vehicle has enough time to react and can see enough to react timely. Okay, now to the last stage. After the simulation is finished, the results must be evaluated to form a verdict for the test case. And in our case, the evaluation is a post-processing step. The basis is the ground truth trace file saved by the execution. And this is a collection of open simulation interface ground truth messages for multiple time steps of the simulation. A Python script extracts the relevant data from the trace file and saves it as tables of numbers, which serves as interface for further toolchain independent processing. These tables are then used by other Python scripts which compute individual metrics, TTV and PET, and the scripts have been developed as collaboration between our product partners, Office and DLR. Finally, these descriptive results can be used to create a comprehensive test report. And this concludes my part of the presentation. I would like to turn it over to Sonja Marahrens from IPG Automotive. Thank you.
So thank you, Thomas. With the next few slides, I'm happy to shortly explain the context of SUC2 in the IPG Automotive simulation environment CarMaker. The simulation environment CarMaker serves as an open integration and test platform, which combines many aspects of virtual test driving. Several components provided by the CarMaker are used directly to complete the integration of SUC2. One core element is the representation of the whole closed-loop simulation. The scenario and the traffic space are realized, and for this, standardized input formats OpenDrive and OpenScenario are imported to CarMaker, and a suitable representation in CarMaker proprietary formats is generated. On top of the structure and the behavior of the scenario, 3D representations of the environment and the objects, for example, traffic objects and traffic signs, etc., are provided by the simulation environment itself. One key aspect in this SUC is, of course, having an open integration platform. This allows us to integrate custom models via several interfaces. Here, the FMI standard in combination with ASAM Open Simulation Interface is mainly used. Due to this modularity, it is possible to replace the internal vehicle dynamics model and to build up a complete closed-loop simulation out of external models. The visualization in IPG Movie allows to observe the simulation, to generate a vivid representation, and to export movie files for playbacks. Last but not least, in SUC2, a total of 400 scenario variations was generated, leading to the point that test automation becomes an important component. The scenarios can be simulated automatically here, and the user-defined scripts can be integrated to generate suitable output for post-processing. Next, I will explain the implementation structure more detailed. First, we have the pre-processing, on the left. Standardized input formats OpenDrive and OpenScenario are imported and represented in the CarMaker proprietary format. In combination with other input data such as 3D models, this data is displayed in the lower part of the slide. It is accessed by the simulation program before and during the simulation via a proprietary interface. The most present components for the user are the main GUI and the IPG Movie. In the main GUI, the imported scenarios and road files can be viewed and edited with the scenario editor. With the test manager, the test series can be defined, associated scripts can be linked, and all variations can be simulated in once. The IPG Movie is there to visualize the simulation. In this integration, this also includes a visualization of the sensor model outputs, and an example of this will be shown in a minute. Simulation program, so the CarMaker executable, is the core component that handles the whole simulation and processing of all calculations. The proprietary models, traffic and environment, are calculated here, for example, to follow the given trajectory of the scenario. An extension of the core product is used here that provides the standardized open simulation interface by mapping and transforming CarMaker internal quantities. Our C-code interface is used to handle and map OSI quantities to replace the vehicle dynamics model with the quantities given by the Fraunhofer vehicle dynamics model. The ASIM Open Simulation Interface is primarily used to integrate the models provided by our project partners. These models are given as FMUs. 3 sensor models, a camera, LiDAR, radar, a vehicle dynamics model, and a motion control model are arranged around the SUT. The SUT is the highly automated driving function, and this is integrated via an FMU that creates a TCP connection and exchanges OSI messages during the simulation. The SUT itself is capsulated in a Docker container, which is pictured by its console output on the right upper part of the slide. The post-processing can be seen below that. During a simulation, predefined quantities are written in a log file, and using a Python script developed by DLR, the KPIs, TTB, and PET can be calculated and visualized in graphs, also for all variations. For the presentation, now one of the scenario variations was chosen to give an idea of the simulation results. In the following movie, the ego vehicle is driven by the highly automated driving function, the SUT. A text box next to the vehicle also shows information about the detected moving objects by the sensors and the distance between the ego vehicle and the pedestrian center of bounding boxes. The objects detected by minimum one of the sensors are highlighted with transparent boxes around the objects. Note that the dimensions of the highlighting are directly given by the sensors, so if an object is not completely in the field of view, or the sensor just partly recognizes it is, the detected object size might differ from the original object size here. On the upper left part of the movie, you can also see the ego velocity, and since it's an external vehicle model, the gear information is not provided here. Now you can see the video, and the truck here is turning left very late, so the ego has to react on this, and afterwards can turn right, with reacting also to the pedestrian. So after this demonstration of the SUC2 realized in CarMaker, I thank you for your attention and hand back to Martin Fischer again.
Coming to the results. The table shows 5 exemplary parameter sets. The first 2 sets, number 7 and 11, are the ones just demonstrated on the last slides. The additional 3 sets represent further interesting variations in the resulting situation. All 5 sets are representative corner cases for the tested parameter ranges. Please note that all in the following presented figures represent the simulation use case 2 evaluation without being qualified to serve as a general assessment. The results for the PET evaluation for all 5 runs show that the test in all cases was successful, which means a PET value bigger than 0. In fact, the PET values for all runs are quite similar. Hence, the parameter variation seems to have no influence on the resulting PET in this scenario. Concerning the TTB, 2 different braking intensities were considered. A soft intervention with -2 meters per second squared and a hard braking maneuver with -7 meters per second squared. Both TTB signals are plotted for the demonstrated simulation runs 7 and 11, the purple and the brown line in the diagram, together with the ego vehicle speed in green and its acceleration in blue. You can observe that for the time around T1, when the ego vehicle reaches the intersection, a clear difference can be observed due to the variation of the ego starting position. When the ego starts closer to the intersection in run 11, it has to reduce the speed almost to 0 because of the truck, which is still at the intersection. This is not the case for run number 7. You could see this in the demonstrated videos. During the most relevant phase, shortly before T2, when the pedestrian leaves the crosswalk, the highly automated driving function acts similar, and TTC values are in both cases uncritical. From the overall safety assessment point of view, the TTB should never reach 0 until T2, at least for the metric A brake 2, assuming hard braking. This is the case for all scenario variations. However, from the perspective of the pedestrian, the phase between the ego vehicle entering the intersection and the pedestrian leaving the street, which is T1 and T2, is mainly relevant for the perceived safety. Thus, the minimal TTB analysis focuses on this phase. Here, the overall results of the minimal TTB for the relevant phase between T1 and T2 are shown. For all selected simulation runs, the TTB never goes below 1.6, respectively 2.5 seconds, which means that the highly automated driving function always had the situation under control with a good margin to react on unforeseen changes. In order to classify the criticality, the minimal distance between the ego vehicle and the pedestrian has been investigated as well. The distance calculation takes the bounding boxes between the two road uses into account. It can be seen that the minimal distance during the relevant phase between T1 and T2, here shown for the soft braking and for both the soft braking and the hard braking, is never less than 8.3 meter, and for the hard braking never below 7.7 meter. For scenarios 11, 102 and 122, where the ego starts close to the intersection, the parameter variation has no influence on the resulting minimal distance. For scenarios 7 and 38, small differences can be observed. Here, the different waiting time of the pedestrian seems to influence the outcome, but only to a small extent. Subsuming the results, 5 manually chosen parameter setups have been analyzed using PET and TTB as metrics for the performance of a highly automated driving function as the system under test. It can be concluded that the highly automated driving function for the chosen parameter setups always acted safe with good safety margins. Though it has to be pointed out that the result does not allow for the evaluation of the suitability of the parameter ranges or the appropriateness for the validation process. This topic will be taken care of in the already running project V&V Methods. You will learn more about this project and its connection to set level later today. Furthermore, some differences in the ego behavior between the two applied simulation tools could be observed. Possible reasons could be inconsistent or incomplete standards or not sufficiently defined requirements. Here, a thorough investigation of the causes will take place in the future work of the project. However, the main goal for the current work was achieved, and the results do serve as an exemplary demonstration of the effectiveness of the composite simulation system. Without going into too much details, this slide shall display how different working groups in the project contributed in various ways to the overall success of the development of SUC2. Thus, the demonstrated results are based on the joint effort of all the project partners. SUC2 implemented and demonstrated an exemplary closed-loop simulation for integration testing on the basis of state-of-the-art standards, namely FMI, OC, Open Scenario, and Open Drive. We could provide feedback to standardization committees. For example, the current extension of OC 3.1 is already influenced by set-level project results. Furthermore, SUC2 established a modular simulation tool chain. We applied harmonized interfaces and demonstrated a flexible model exchange between different companies and simulation tools. As considerably shown in this presentation, SUC2 demonstrated the closed-loop test of a specific highly automated driving function in interaction with sensor and vehicle dynamic models using dSPACE and IPG automotive software-in-the-loop toolchains. SUC2 contributed to the discussions around scenario generation and evaluation metrics with applied functionality. And last but not least, SUC2 applied the credible simulation process. On this basis, the simulation development process obtained a project-wide uniform structure, and it enables traceability, which will be a topic for the further course of the project. Which directly brings me to the concluding remarks about the goals for the remaining part of the project duration. We plan to examine different aspects regarding simulation quality in order to contribute to confidence and performance criteria. We will further work on simulation automation, especially by looking at the SSP standard for the description of simulation setups. And, as remarked before, SUC2 will serve as an example for the aspect of traceability. Within the scope of SUC2 application, we are going to implement a test scenario comprehending fault injection, and we will investigate whether current communication and scenario description standards cover this test case, or how they have to be extended to do so. Finally, we are aiming for a knowledge transfer beyond the project consortium and the project duration by subsuming the results in public deliverables and implicit by the improvement of tools and standards, as already done. Furthermore, some of the set-level models will be published open source. Thank you very much for your attention and your interest in the presented topic. Now, my co-presenters and I are happy to answer your questions.
And there have been quite a few questions, which is good. Many of them refer to the models and the interface. So let's start with the first question about the interface between the FMUs for communication in the simulation environment. Are they based on an open source standard?
Yes, the open source standard we used is the OC communication standard. I can shortly show the architecture picture again. Wait a second, here we have it. So you see the arrows in the lighter blue. Here we used original OC defined standards. and filled them with the content of the simulation or the model content. And the arrows in a little darker blue color, there we followed the same formats as the OC standards, but here no standardized signals were predefined, so we defined our own communication signals. But all light blue arrow signals you can find when you look at the FMI standard, the OC standard at the ASIM homepage, which is referenced here at the bottom of the site.
Yeah, and while we are on this slide, the point which has not been quite clear in the presentation, the HID function itself was not implemented as FMI. Was it impossible, or is it something we just didn't do?
I'm not 100% sure about that. Probably you would have to ask the FZI implementers for that. I think it was due to the fact that it's based on ROS, that it wasn't that easy to integrate it as an FMU, that they chose to go this way. In fact, at another point, it turned out to be not that easy out of the box to make a model into an FMU, for example, for Simulink models. The developers of the motion control and vehicle dynamics struggled quite a time to make the Simulink models run as FMUs. So there are probably technical reasons, but you can have a look into the virtual cafe and have a look for Mark Heinrich, who is the developer of the highly automated driving function. And if he's there, you can ask him directly. He will probably can give a more detailed answer.
Okay, then there's a follow-up question, which for the OSI question, which version of OSI did we use? Well, I think I can answer it. It's based on 3.2.1, no, 3.2, 3.2.0, and we made some adjustments, as you mentioned. Then there are some questions regarding the sensors and the fidelity. So we have been using middle fidelity models which are object-based. Are there sufficient benefits, or would there be sufficient benefits in using high fidelity ray tracing sensor models? Well, there's obviously an additional overhead. Could it be compensated? What are your thoughts?
Yeah, good question. There's explicitly the difference between the simulation use case 2 and 3. So if you want to have a look afterwards at the presentation of a simulation use case 3, there the physical models will be used, including ray tracing and all those physical aspects. Here we choose to use sensor models on the object level due to performance reasons and to realize an real-time simulation. The second aspect was that here more the closed loop interaction between the different functions was in the focus. So therefore we choose to pick object-based models on this level.
Okay, and then another question regarding the sensor models. So, well, it's the question is, did we? Okay, well, you partly already answered it. Did we use it because OSI does not support ray tracing information? Is our reason, and do we consider to go beyond object-based models?
Yeah, partly I gave the answer. In simulation use case 3, we explicitly look at the at the different sensor models on a physical level. So there we're looking at the sensors from that perspective, and of course the colleagues try to look at the signals, and if they come to an input to the standard of OC communication, and they come to a conclusion which extension for the standard could cover even physical based models, we will provide it to the OC consortium.
Right. So then there's another question regarding the HIL use case, hardware in the loop. Do we perform hardware in the loop simulation? Do we support HLL standard or just FMI?
We did not explicitly use hardware in the loop testing here, but looking at the highly automated driving function in a similar way within Gateway, this could be done using this architecture. This architecture allows for a distributed system execution. So hardware in the loop could be a use case for this. Yes.
And then there are two questions which are targeted at Sonja, IPG Automotive. So the first question, the FZD vehicle model, which uses OSI, replaces the internal car maker vehicle dynamics model, right?
Yes, that's right.
That's a short answer, but yeah. What has been asked for. And another question, is IPG planning to support cloud-based computation?
Actually, I can't say anything about the planned actions, but as far as I know, in the current releases, there are options for that. And I there have to to please you to have a look at the documentation of the current releases, and there you will find further information on this.
Okay, then back to Martin. So one question is about uncertainty management. Did we apply uncertainty management techniques to investigate the importance of model parameters on variability of simulation results?
No, actually, we didn't take that into account so far. The focus in this phase really was on the application of the standards and the integration of the models into one combined simulation system. But maybe this could be an aspect for the further work in the project run. So I will take that as an remark with me, and we will discuss that.
Okay, then another question. It's not really simulation use case specific. It's more on the project level. Seems like tier 2 companies are not involved in the set level project. Do you know the reason, and do you see a reason why we should include them in the future?
Well, yeah, of course, there is an obvious reason to maybe involve them more, even though Bosch at least was involved as a project partner, but probably that could be extended. And the reason is that what we're doing here should serve as a base for OEMs and Tier 1, Tier 2 companies as well as a common basis for future cooperation. So the more project partner or partners coming together and discussing these topics and working on solutions, the better, I would say. But I'm not aware of the reasons how the consortium was formed. So that probably you better have to ask in the virtual cafe, Mr. Köster or Mr. Rude.
Then there is a follow-up question regarding hardware in the loop. So on the HLA topic, high-level architecture standard, which is mandated by the US Department of Defense. Well, we didn't consider it, right? Not part of our scope.
Yeah, so you more or less gave the answer. No, we didn't consider it. I mean, there's the HLA standard and other protocols like the DCP in order to build up a simulation via network. So more distributed simulation than we looked at now. But so far we didn't consider this. No.
And then there's a last question about the time sync between system under test and the simulation system for both tool chains. Well, so I can answer for dSPACE. It's basically a blocking connection. So the message from the simulation system to the HID function is waiting for the response, and thereby it is synchronized. Sonja, do you have something to add?
No, thank you. That since we use the same approach for the network proxy, I can just yeah, that's the same answer for the IPG realization. Yes.
And thereby it's also deterministic. Yeah, so that's all, I think. Martin, do you have some parting words?
Yes. Again, thank you for your attention and your interest and the questions. If you have further questions, I can again refer to the virtual cafe, which will be open during the breaks and especially after the final presentation. So yeah, join the virtual cafe and place more questions there. Now we will facing a lunch break for everyone. So maybe some attendees will be from time to time be in the virtual cafe, but I think it will be lunch break for the presenters as well. So we will join again at 1 o'clock. So come back at 1 o'clock, pick from the agenda the topics you are interested in and pick the right stream. Then we will start on again at 1 o'clock. So have a good lunch break yourself, and then I hope to see or hear you again afterwards in the continuing event of today. Thank you.